Hello there. Today, we'll be talking about implementing the deref and drop traits. Let's get started. In the smart pointers and box video of this playlist, I told you that smart pointers are usually structs, and that one of the things that distinguishes them from normal structs is the fact that they implement the deref and drop traits. But what does that even mean? So let's take a look at some code. In this snippet of code, you see a normal pointer being dereferenced. Nothing new here, but the reason I'm showing you this is to highlight what we want users of our smart pointers to be able to do. So let's see if we can do this with a box. Alright, so let's just quickly create a y1. It'll be box new around x, sort of mirroring the first y, and then we'll do an assert equal on 5, and we'll dereference our box. Awesome, let's save this, bring up our terminal, and cargo run. Cool. Now, running this code, we see that both assertions were just fine, thanks to the box, and that's the box's implementation of the deref trait playing true. Now, let's create our own smart pointers so we can see what implementing this deref trait looks like. As you can see here, I've deleted our previous introductory code and created a new struct that I've called myBox. MyBox is supposed to act as a copy of an actual box smart pointer, but it doesn't do much right now other than just its definition and a function to create a new myBox instance. So let's just rewrite our introductory code but using myBox instead. Now, if we try to compile this, we'll see that we get a compilation error saying that myBox cannot be dereferenced. And myBox cannot be dereferenced. So let's change that now by implementing the deref trait. Okay, so for easy access of the deref name, let's use a use declaration for std ops deref. And next, I'll quickly write the implementation. We'll go over it, but then we'll take a quick aside because it has something that I have not introduced to you all yet, which, if you're looking at the screen right now, you should be seeing it pop up. Anyway, almost finishing up. Just writing the actual function. Okay, so let's go over it. Going over the very first line after, of course, the implement. There it is. As you can see, the first line already contains new syntax. That is what I mentioned. It's called associated types. So let's take a quick aside. Okay, so associated types is a syntax made to improve the overall readability of code. To show you what I mean, let me write up a quick example. Okay, we'll start off by creating a tuple struct called pair. It will have two i32s like that. Next, we'll create a trait called coordinate, and we'll have A and B. And this trait will have two functions. It will have a function x, which takes in self and returns an i32, and then a function y takes in self and returns also an i32. All right, next up, we'll do an implement for coordinate i32 for pair. and we'll assign our first element to be the return of the x function, just like so, self.0, right? Because we're accessing a tuple struct. Next up, we'll do the same thing for y. Obviously, nothing too new here. I'm just sort of writing out the basis for the explanation of the aside. Okay, cool. Next, we'll create a fully generic ydif function to subtract two coordinates. So we'll say function ydif, and we'll have a, b, c, and it has a, b, c because we'll pass in a coordinate 1, c, and a coordinate 2, also c, and we'll return an i32. And then where c is a coordinate a and b. Now hopefully you're starting to see sort of what I mean. Next we'll do a coordinate 2, but if you're not, don't worry, I think it will become clear in a minute. A y, and next up our main function. Also note that to avoid clutter, I commented out the previous main function. Anyway, that said, we'll create two coordinates. Coordinate 1 will be a pair 1, 2, and coordinate 2, which will be a pair 3, 4. Cool. Then we'll use the debug macro to just call ydif on coordinate 1 and coordinate 2. Let's not forget our semicolons. Cool. Alright, oh, I just missed an F here. Let's save this, and now, just for fun, let's run this code. So we'll do a cargo run. I don't want to show anything crazy here. Oops. Looks like I added random m. Now let's run it. And there it is. So just what we expected. And if you didn't know what the debug macro does, there it is. It also prints what we're printing. As you can see, because of coordinate being generic, ydif must explicitly state all of the generic types. And that can get quite messy. So to improve upon that, as you can probably guess, we can use associated types. Now let's rewrite our coordinate trait implement and the ydif function with associated types. Alright, so first we'll come up here and we'll remove the generic markings, and we'll create a type A and type B to make use of associated types. Next, in our implement, again, we'll remove our generic markings, and oops, I clicked page down. We'll create our associated types. So A will be of i32, and type B will be i32 as well. This way, now for our ydif function, we can say, instead of ABC, we can just say C type coordinate. And that's it. We can remove this where. And it's much, much cleaner. Now, obviously, we can run it too just for fun and see that nothing has changed, but our code is much cleaner. Alright, I hope this gave you some clarity over associated types and consequently over the implementation of the Deref trait. So, talking about the Deref trait, let's get back to it. Alright, so on commenting the main code and commenting the aside code, we can see we left off right after having implemented the trait. So let's go over it. As you can see, we have an associated type called target, which you should understand. And next up, we have a member function called Deref, which returns a reference to type T. And it does that by accessing the 0th element of our tuple struct, myBox. Now, something you have to understand is that whenever Rust sees a variable of type myBox, so say the DerefY, it will actually substitute that DerefY with a call to the function deref inside of y. So it would look something sort of, say that Rust sees this, it would actually change that to be something like this. So y.deref. Okay, so it's calling that member function and then dereferencing the reference T. All right, so now let's test that by running our main function again. Here we'll say cargo run, and there it is. It finished running just fine, so the assert passed. And that's how you implement the Deref trait. Okay, so Deref coercion is when Rust converts a reference to a smart pointer that implements a Deref trait into another reference. So like, I don't know, a reference to a string, which we know it's a smart pointer, to a string slice, right? So it would be that reference str. So that is a string, implements the Deref trait in such a way that it returns a reference, well, string slice. Okay, so that is, we can do something like this. Let's implement a function called, I don't know, hello. We'll take in a name with an str, write a string slice, and we'll just print line hello, oops, and then the person's name. Ryan will pass in the name there. Cool. Now let's just write a quick main function. And in the main function, we'll create m of type string from Rust. And now we'll pass that into hello. Now, running this, we see that we get no mismatch type errors. That's cool, and that's Deref coercion, and probably the most common example of it, I would say. However, I want to show you that this goes even farther. So, that is, instead, let's make m of type myBox string. So we'll say myBox new, and then oops, string. Cool. Now running this, we see that Deref coercion works even with this sort of nested structure. We could even add one more myBox new outside of that, and Deref coercion would still play its role. Now this is cool because if we didn't have it, we would have to call the function with something like this. We'll have to explicitly dereference out of myBox, then get a string slice for string, and then get the reference. So yeah, pretty cool. I've showed you how to implement the deref trait, but that doesn't tell the full story about the dereference operator. For example, say that we wanted to do something like this. We want to dereference out of y and then change its value to 10, right? So then the assert would fail. If we run this code, so let's do a cargo run, we'll see that it complains to us that, DerefMut trait is required to modify a dereference. So that said, it can be very easily implemented like so. We'll just say, let's just do it right here. Minimize our terminal. We'll say implement coerce type t DerefMut for my box, again type t, and we'll say a function DerefMut self, and we return out this time mutable reference type t. Now this part is pretty similar, just say mut self dot 0. Main difference, we're borrowing as a mutable reference and then returning mutable reference like so. Now nothing too new here. So if we run this code, I forgot to bring in the DerefMut. Oops, I have to make this mutable. There we go. Obviously, we panicked, but that's just because the assert isn't the same, right? Well, anyway, that said, that's all I wanted to cover about DerefMut. Now let's finish our talk about deref with one final closing remark. Deref coercion obviously also works with mutable references. And the way it works, I think, is pretty intuitive. So if we have reference t and the coercion, we can only get a reference u as the coercion target. But if we have a mutable reference t, we can either get a mutable u or an immutable u. So that is, from an immutable reference, you can only get an immutable reference. But from a mutable reference, you can get a mutable reference, or you can get either a mutable or an immutable reference. That's it. Now let's talk about the drop trait. Now, the drop trait allows you to customize what happens when one of your types goes out of scope. So let's make a simple type and implement the drop trait for it. So we'll say struct whatever, and this is very much like our box type, but not generic. Will be of type i32. And we'll implement drop. The drop trait is included in the prelude, so we don't need to import anything for whatever. Now we have drop, which is a member function, and it takes a mutable reference to self, like so. Now in the body of the function, the only customization we're making is that we print line a message. So we'll say dropping whatever with data, and then we'll do a self.0. So we'll print a message showing the data that was contained in the whatever that was just dropped. Now we'll have a main function quickly, and in main we are just creating two whatever instances. So we'll say let a whatever, I guess we don't have a new, right? So let's just do 1 and a let b whatever 2. I'm including the underscore, otherwise Rust will show warnings that they're unused variables, right? Now let's bring up the terminal. And when we run this function, we'll see two messages showing up. It's cool to note that they are dropped in reverse order of creation, right? So we created 1 and then 2. So it drops first 2 and then 1. Cool. Now, before finishing our discussion on drop, I wanted to have one final closing note. We're never allowed to explicitly call the drop member function. So is it even possible to drop values early, right? Like before they go out of scope? And the answer is yes. We do that by using std_mem_drop. So looking back at our example, we can do something like this. Come up here and we can say std_mem_drop, and we'll drop a there. Now let's run it, and there we go. We see that it worked because A was dropped before B. And with that, we are done. That about covers what I wanted to go over in this video. As always, thank you so much for watching. And if you followed the channel for a while, thank you for sticking around. The past couple of months have been tough for me, and that made posting videos much, much harder. In any case, I'm glad to be back, and I'll see you in the next video. Bye-bye.